you doing?
Good, how are you?
Good. I heard, yeah. Our quiz is going to be a bigger quiz.
That is true.
It's sad.
But you have more time for it.
Yeah, that's true too. How you doing, Blake? Pretty good, Well, pretty good. You're going to be on our money here. You chess. Very funny meme up there.
Yeah, you like that one?
It's alright. It's good.
I had a student send me that one.
Did you see my cornhole I brought in? No, not today. But yeah. Did you get a haircut? Yeah. Well, it looks like you got more than a haircut. Yeah. I feel like I've never seen your hair different, Mr. Townsend.
Yeah?
It's always been the same.
Do you expect me to just radically get different haircuts at my age?
Well, like, I feel like you would grow it out a little bit, cut it, grow it out a little bit, cut it.
It's
Not
pretty
just, like,
long.
cut it
You want him to
every
grow it
week.
out?
It's pretty long in the back.
He's growing it out right now.
No.
See
Grow
it?
the mullet.
Yeah, that's gonna be mine if you throw it again. So.
Oh, okay. Yeah.
It's 4 pi.
You want me to just turn in the papers?
Yeah, you can.
See, what I did was I took the papers that I was supposed to have in here, and then I set them on my desk in the next period.
Well, that didn't help you out there.
I don't understand the meme.
It's at 120 degrees.
Oh, I see. Okay.
What did they look like?
I'm pretty sure 120 degrees is like.
I was like, wouldn't you do it way warmer?
Yeah, like, I don't know.
Whoever made that.
Just a joke.
Is that 120 degrees? Yeah.
Sort of, yeah.
So if you baked it at like 270, would it just be upside down?
Yeah.
Just make a mess. I don't know. Someone sent me this one.
Do that 180 degrees. And
Some of my calculus students. I don't know. They're happy if I use their memes, so it saves me time for making them or finding them. I don't make them.
I like the one about the first day of school.
With the
Do
big
you remember that
backpack.
one? Yeah.
Yeah, I use
That's
that
so
one every
true.
year. I can't believe you remember it though.
I just remember it because I related to it. It was like pretty accurate.
Alright, we got more school business today.
How you doing?
In school business. Raven school business. Diego. Luke. Everybody else is
Make it
Someone forgot my backpack in my car.
My battery is low.
just what do you need for right now?
A pencil from whatever
Can't
I'm
risk
working
it.
on.
Just borrow one of these for right now. You can
Hopefully
get
it
it after we
survives.
find something.
Let's
Okay,
send it
we've
to
got
zero.
a bit of a change in our schedule here, so I guess this is one downside of not seeing you guys since last Wednesday. But we did decide to not do a quiz over just 1.1 like I had told you there was going to be. But that stuff So hopefully you studied for it and you feel ready for a quiz. So a later quiz will have those type of questions, plus some of what we're going to do today. So it's not for nothing, but it's not going to be just a quiz today. And so today we're going to spend one full class period on solving quadratics. So we're going to talk about the different methods, review how to simplify radicals, and then focus mostly on some of the harder quadratic formula type questions, because if you can do those, then you can do any of them. Okay, so today's handout is 105, and even though we're not doing the 1.1 quiz today, I will still ask for those 3 assignments. I know a lot of you already turned them into Google Classroom, but if not, I ask that you turn them in at the end of class, the hard copies, please. So, solving quadratics. Alright, so your first page, we're going to just talk about some different methods that can be used. There's actually 4 methods, but 2 of them are very, you don't usually get to use them. 2 of them are pretty strong and 2 of them are just rare instances. So method 1 is if you have some x squared stuff, which makes it a quadratic, but you don't have any x's, then you can just solve this like normal. Now today when we talk about solving implies that you're trying to figure out where it equals 0. So we're trying to find all the solutions to this equation. So again, if you have x squared stuff but not x stuff, then you can just do subtract with add, undo subtract with add, undo times with divide, undo times with divide. And how do we get rid of a square root? Or, never mind. Square root, both sides. I said the answer, not the question. Now, my one concern with you right here is that I think you know the square root of 81 is probably 9. The square root of 25 is 5. But what am I missing out on these questions?
Plus and minus.
Right, and if you take the square root of both sides, if you're solving an equation, you've got to do plus or minus. So it's not just 9, it's 9 and negative 9. It's not just 5, it's 5 and negative 5. Quadratics can have one solution, and quadratic equations can have no solutions, but most of the time there should be 2 solutions. Now, this isn't going to come up anymore today, but anytime you have x squareds and no x's, you can just do this method, as long as you don't forget the plus or minus. Whereas the second method is my favorite, so I'm going to put a star by it. Factoring is usually the quickest way and what I always lean towards. So if you're going to take the factoring approach, sometimes you need to check your work by foiling. On our last test, I think the majority of the people that tried to factor one of the questions did factor it correctly. However, I think it probably was still the most common mistake, was the not factoring it correctly. Remember, you can always foil your answer to make sure it goes back to what it starts with. And the nice thing about factoring is then you can set this equal to 0 and solve, set this equal to 0 and solve. You got both solutions. Set this equal to 0 and solve, set this equal to 0 and solve, and you got both solutions. So if you are good and comfortable with factoring, that's usually the quickest method. But it can't be our only method, because factoring, not everything factors. Okay, our third method is with graphing, and this one is very case dependent as well, because you really need a calculator. So when I want to know when this equals 0, I'm basically saying when y equals 0, and where on the graph is y equals 0? What do we call that?
X-axis.
X-axis. The horizontal line that is the x-axis. So what we're really interested in here, if we want to know where this equals 0, so we want to know when y equals 0, we're thinking about x-intercepts. So x squared plus x Was it minus 20?
Yes.
Okay, so you don't have to graph this in your calculator, but do a quick little sketch. It goes through 4 and negative 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Those are the places where y equals 0, which is the same thing as f of x being 0, which is like solving this.
We could have factored that, couldn't we?
Yes, but we're just trying to focus on different methods. Right now we're just talking about factoring as an option. Now after this one more of these, factoring is not going to be something we look at today, but I still put it on this sheet because especially the ACT, like if you guys just need a quick answer and you have a calculator, then sometimes this is the quickest, even if you can factor, even if you can do quadratic formula. Okay, what was the next one? Negative x squared plus 11x.
Minus 28.
Minus 28. So draw a quick little sketch here. Solve this by graphing. F of x is the same thing as y, so it equals 0 at the x-axis. 1, 2, 3, 4, and 7. 2, 3, 4, 6, 7. Okay, so I don't know if we've used that method any this year, but I assume you guys are okay with that. We can keep going. Okay, and then the big one, and this is where we're going to spend the majority of our class time today on, but we're not going to work these two out. But what I want you to see is that this is the one, quadratic formula is the one that always works. Sometimes a graph doesn't work because you don't have a calculator, or maybe it's got a decimal answer and you're expected to give an exact answer. Sometimes factoring doesn't work because not everything factors nicely. The method 1 at the top isn't going to work if you have x's in addition to x squareds. It works only if you have x squareds. So if you're only going to be good at one method, it has to be quadratic formula because it's the one that always works. Now it's more work than factoring, which is why we try to avoid it, but it is nice to have as a backup plan. Okay, so before we get into the quadratic formula, and on page 3 we'll slowly build up from the easiest type of quadratic questions to slightly harder questions. Within the quadratic formula, we're going to need to be able to simplify some radicals. Okay, so I think you can give me the answer to this top row. Square root of 25 would be what? And then square root of 16. And finally, okay, those are all perfect squares, so those all work out nicely. But let's stop for a second and think about why these were working out. 25 is 5 times 5, and because we got two 5s, it simplifies to 5. Square root of 16, you can think of as square root of 4 times 4. You got two 4s, so it simplifies to 4. Square root of 100 is like 10 times 10. Square root of 79 is like 7 times 7. That's why those work out the way they do. Because 125 is not a perfect square, that doesn't mean that we can't simplify it. So we need to break this guy down, and I'll show you another method here in a minute. But of the two methods I'm going to talk about today, this is by far the one I think is more useful to you. So I'm going to do a factor tree and rewrite this question into something called its prime factorization. So a factor tree just means you try to find two numbers that multiply to 125. I'll do 5 and 25. If something is prime, you quit, and if something's not prime, you have to break it down more. But what I need you to see is that 125 is the same thing as 5 times 5 times 5. So just like the square root of 25 works out this way, if we've got two 5s in here that can group up, for this pair of 5s, they can group up and come outside of your square root, and then this 5 that had nobody to pair up with gets left behind. So square root of 125 needs to be changed to 5 square root of 5. To do the same thing with 27, What is two things that multiply to give us 27? Okay, 9 and 3. 3 is prime, so we quit. 9 is not prime, we have to break it down more. But the prime factorization of 27 is 3 times 3 times 3. So because this is a square root, just like a lot of times in mathematics, we have what's called like invisible math. When I say x, you know that this is 1x, right? And we understand that the exponent is 1. There are certain things that we just don't always write. Well, with square roots, there's an understood exponent of, or index of 2, which means you need 2 of the same thing to group them up and bring them out. And then if there's something left behind that didn't pair up with something, then it gets left behind. Everything that comes out gets multiplied together. Everything left behind gets multiplied together. So h, you could do 2 times 4, and 4 is 2 times 2. So instead of calling this the square root of 8, you could call it the square root of 2 times 2 times 2, which gives us what as an answer? Good. 2 of these, make 1 outside, 1 left behind. Okay, let's do one more this way, and then I will show you a way that you can kind of check it with your calculator, just for future knowledge. I don't think you really need it today, and I'll show you one more way that you may have learned this in Algebra 2, if you prefer to use that. So 12 is like 3 times 2 times 2. So this would be 2 square roots of 3. Now, one thing that you can do to help yourself check this, it doesn't guarantee that you simplified it completely, but what we can do is we can ask our calculator what is the decimal of the square root of 12. And then let's say I thought it simplified to 3 square root of 2. You can see that these are not the same thing. When we simplify a radical, we're not trying to change the size, we're just trying to change the appearance. So if nothing else, you would say, wait, I made a mistake, let me do some more work, and then eventually maybe you get to 2 square root of 3, and then you can see that's equivalent. So you're not changing the size, you're just changing the appearance. Now again, that doesn't confirm that you really simplified it all the way, but it does help you catch some mistakes. Now, in Algebra 2, did y'all ever talk about cube roots and fourth roots or fifth roots? You did? Okay, good. So the reason why I really like prime factorization, because if you want to do a cube root, you just got to get 3 things of the same type to bring one out. If you want fourth roots, you need 4 of the same type to bring one out. Fifth roots, you need 5 of the same thing to bring one out. So this factor tree prime factorization is very easy to adapt to the other methods. That being said, some of you learned it this way in Algebra 2, and this will be good enough for the quadratic formula. Instead of calling this the square root of 12, we could call this the square root of what times what? And the reason why you might think of it as the square root of 4 times the square root of 3 is because you know this in your head, and hopefully you recognize that this can't be broken down anymore, and you end up with the same answer. So that's fine for square roots. It just doesn't trickle over into cube roots and fourth roots as well, which is why I'm not a big fan of it, but it'll be fine. Okay, I'm skipping this last row because I want you to do a couple more of those at the end of our notes here. So let's skip down to 21. So occasionally with quadratic formula, you may have no real solutions, no x-intercepts, and instead you have some imaginary solutions which don't show up as x-intercepts. So there's really only one additional step that you have to know, and it is this one. The square root of -1 is defined as the number I. So if you can simplify the square root of 4 to be 2, the square root of -4 is just 2i. In fact, I would just always bring out the negative first. A negative under the square root comes out as an I. The rest of the square root reduces the same way. Negative under the square root comes out as an I. Square root of 81 is still 9. unfortunately, we probably won't have time to review much with imaginary numbers, but at least simplifying radicals is pretty simple. So let's look at one more row together, and we'll save the last row for you to come back and do. Now, the bigger a number is, the harder it's going to be to break down. So if you try to do like the perfect square method like this, square root of what times square root of what gives you the square root of 216. That's a little bit harder to do, especially trying to get the biggest perfect square. The factor tree, as long as you can find one thing that goes into it evenly, your numbers get smaller, which then your numbers get smaller, and then it should be getting easier and easier. So I think factor tree is a little bit better. And before I forget, I really should bring this negative out as an I. And then 216 is 2 times 2 times 2 times 3 times 3 times 3. But it's a square root, so I need things in pairs. So I brought the negative out as an I. I'm bringing out 1, 2, and I'm bringing out 1, 3. Multiply all that together, you get 6i. And then left behind, we have a 2 and a 3. Multiply everything that's left behind, gives you 6. So yes, it takes an extra 20-30 seconds, but it's not any harder just because the numbers are bigger, at least with the factor tree. But the main thing I'm trying to emphasize here is always just pull the negative out as an I before you forget. Then you can worry about simplifying your radical. Looks like 28 would be 2 square root of 7. So the square root of negative 28 would be 2i square root of 7. Pull out the I. Let's see, 2 and 36. So 6 times 6. So 6i square roots of 2. And then one more, and then I will pause for questions to make sure you guys are okay. Pull the negative out as an I. Find two numbers that multiply to 150. Keep breaking it down until you only have prime numbers. Looks like you could pull out a 5 and leave behind a 2 and a 3. So 5i square root of 6. Okay, so I'm going to save 4 of them that don't have I in them on this page for you to come back and do, and then the last 4 that you should have I in your answer for you to do. But do y'all see anything specific about this that you'd like to ask before I move along? Do y'all remember this part pretty well? Yes? So we probably didn't need to do this page?
Yes.
We did need to do it?
It's a good refresher.
Okay. I'm just trying to decide if I should cut it out for next year. You guys already have it done. Well, except for a couple practice questions. But okay, so moving on to page 3. So here's where we're going to get into the bulk of it. All of that was really to help us build up to the quadratic formula, which we avoided on the first page, but I did point out to you is the only one that always works. Now, quadratic formula questions can certainly come in different difficulty levels. But step 1, memorize the quadratic formula, is the same whether it's an easy quadratic formula question or a difficult quadratic formula question. So negative b plus or minus square root of b squared minus 4ac all over 2a. You need to identify a, b, and c. So you need it in standard form, which means everything on one side equal to 0. A is the coefficient of x squared, b is the coefficient of x, and c is going to be our constant. That's not going to be any harder for any of the questions, just identifying A, B, and C. But then what can be more challenging is this step 3. Some of these questions require very simple simplification, and some of them take a couple more steps, and you kind of have to practice and train yourself for that. So with question 29, we're going to start off with the easiest ones possible, and then we'll slowly build up. Okay, so this is already in standard form, so I can look at here and see A is 1, B is -10, and C is -11. Honestly, if I was you, I would probably write down the quadratic formula every question until you feel like you have it re-memorized. But opposite of B, plus or minus the square root of B squared minus 4AC all over 2 times A. And now, so that's the part that's going to be the same level of difficulty no matter what type of quadratic it is. Formula is the same, picking out A, B, and C is the same, plugging in A, B, and C doesn't get any easier, any more difficult. But the simplifying, so the denominator is usually easy, in this case 2 times 1. Where you need to slow down is this. This stuff under the square root is called the discriminant, and 90% of the time, students who can do the quadratic formula, that I can see their work and see that they can do it most of the time, if they miss something, it's usually the arithmetic right here. So this is like 100 plus 44. I'm just saying, don't rush through that part, because that is a lot of careless mistakes. Now, the reason why this one works out so nicely is this is a perfect square. It's 12. So one answer is going to come from 10 plus 12 over 2. And one answer is going to come from 10 minus 12 over 2. So it looks like we get 11 and -1. Now again, notice with those answers, that tells me factoring would have been much easier, but again, we're practicing quadratic formula here. So
Didn't we establish that B was -10?
we did.
So how'd that go away?
Where? Right here it's B squared. -10 times -10 is positive 100.
The 10 plus or minus, would that be negative?
Well, that part of the formula says opposite of B. So if B is -10, you write it as positive 10.
Gotcha.
Okay, one more that should work out about the same difficulty. So memorize quadratic formula, go through and identify A, B, and C. Plug in A, B, and C as the formula tells you to. Opposite of B, plus or minus B squared minus 4AC all over 2 times A. And then you need to slow down with this stuff under the square root, which is known as the discriminant. This would be 100 minus 84, should be 16. And again, this just works out a little bit nicer because the square root of 16 is not a problem. Square root of 16 is 4. You probably don't need to do a factor tree for that one. But one answer comes from 10 plus 4 over 2. One answer comes from 10 minus 4 over 2. And that reduces to 7 and 3. Same answers you should get from factoring. Now, of course, you could always do this as a backup plan as well if you can't figure out the factoring of a question, but it's going to take you more time. Okay, the next two are going to be a little bit messier as far as the simplifying goes, but the first 3 steps are still going to be identical. We need to identify A, B, and C, and make sure we plug those into the quadratic formula as it says. Being extra careful with the determinant. This is like 1 minus 100 or negative 99. And now what makes this question harder than the last two we did is this is not a perfect square, but that doesn't mean that you shouldn't simplify this sum. So I know I can bring the negative out as an I, and 99, the square root of 99 is like 3 square roots of 11. So that's what your answer would be. One is 1 plus 3i squared of 11 over 10, and the other is 1 minus 3i squared of 11 over 10. And there's nothing we can do to simplify that one. Some answers are just going to look messier. Okay, along the same difficulty, 32. This 1/2 makes it look like it's going to be more of a problem. But you have to know the formula. You have to know where A, B, and C come from. You have to plug those in correctly. You have to be careful with the discriminant. Okay, and then this is like 16 minus times a negative becomes plus. So 16 plus 4 times 1 times a half. 4 times 1 would be 4. Times a half is the same as divided by 2. So this is like 16 plus 2, which would be 18. Make sure you follow order of operations when you do that. And then 18 breaks down. It's just it's not a perfect square. So to me, that's just not much harder, but it's a little bit more. We need to rewrite that as 3 square roots of 2 before we circle our answer. So if you can simplify radicals from the last page, sometimes you need to do it like the last two questions. Sometimes you should probably be able to do it in your head like the top two questions. But okay, and then finally the last type, moving on to the difficulty that you should expect to see from us. 33 is not a great example of that, so we're going to skip that one. I think y'all are seeing enough examples anyway, but so it doesn't look any different. A, B, and C. Plug them all in. (16 minus 8 would be 8. You simplify the square root of 8, it becomes 2 square roots of 2. Do the factor tree if you need to. But what makes these last questions require more work, and why I say they're a little bit harder, is that this goes further. Now, it's a little bit harder to see, but it's like reducing your fraction. The same way you wouldn't leave an answer 5 over 25, you would change it to 1/5, because you can divide this by 5 and you can divide this by the same number. Well, up here, all of these terms, -4, 2 square roots of 2, and 4, all of those are divisible by 2. Just like 5 and 25 are both divisible by 5. So we really need to divide this by 2, divide this by 2, and divide this by 2 before we get our answer. Now when I divide this by 2, be careful not to divide this one as well. I have 2 of these, they happen to be square roots of 2, so if I divide them in half, I have 1 of those. It doesn't change what it is though. And then just for some perspective here, might help you see this a little bit better. You could also imagine out of this numerator that they have a GCF of 2. So if you imagine factoring out that GCF, then you can see that this cancels this and reduces. So that's essentially what we're doing. Just simplifying a fraction. It just looks less familiar. Okay, and then so the same thing should happen on the last couple. So let's try to hone in on that, and then I'll tell you what you guys need to finish up. So opposite of b plus or minus square root of b squared minus 4ac over 2a. Let's see, 4 minus 28 would be negative 24. So the negative I can pull out as an I. 24 is like 2 square root of 6. And what else can I do in this? Every term is divisible by 2, so dividing everything by 2 is simplifying your fraction. Now, when you do that, it puts it over 1. Of course, putting something over 1, we don't really need to write that part. Now, the fact that these solutions are imaginary doesn't mean that they're any less solutions. They just don't show up as x-intercepts. Did I talk about imaginary numbers in here or not? I don't remember.
I don't think so.
Okay, so just to be clear here, most of the time in mathematics, like whatever is the first mathematician to like write up something and get their paper published, they're usually the one that gets to define like notation and stuff. So like when we talk about functions, the reason why we write it like this is because one of the first math people did it that way. So the same thing with imaginary numbers. I don't remember which mathematician it was, but at the time they weren't using them, so he called them imaginary because he didn't think that there was a purpose for them. But then years later they figured out that they really did need them, and we do use them. I think all circuitry stuff uses them, so no phones, no cell phones, no computers, no video game consoles, none of that stuff without imaginary numbers. So even though they're called imaginary, they certainly do exist. Probably should switch the name, but stuff like that kind of sticks. Okay, let's look at one more together. So quadratic formula with a, b, and c plugged in. Careful with the arithmetic on the determinant. Simplify your radical like we did on page 2. If it's a negative under there, just pull the negative out as an I, simplify the rest of it the same way. And then just be careful that your fraction doesn't reduce. 6, 2 i's, and 10 all divide by 2. So you really should divide all of those by 2 before you circle your answer. Okay, I want to give you 2 more hints here before I ask you to do 6 of these on the back, plus the couple of simplifying radicals that we skipped. But you should have more than enough class time for that. One thing I want you to be aware of is sometimes your answers look pretty unfamiliar, I guess. Like normally you may not feel confident about an answer that looks like this. But just like I have pushed you guys to try checking your answers with the calculator throughout the year with the store button, I want to show you that this applies again. So I think this was one of our answers on the last question. Is that what we got for the answer on the last one?
Yes.
Okay. So if I store that in for x, even though it's got an imaginary number in there, your calculator can still do that stuff pretty well. Just you need to know where that I is. It's not this I. This I is for typing a message. It's this I down here. You have to do second decimal place to get the number I. And what that is supposed to be a solution to is 5x squared minus 6x plus 2. It's supposed to make that equal to what? So if your calculator says it's equals 0, then you can feel confident about your answer. If it doesn't say 0, then you might need to ask some questions or check your arithmetic. And imaginary zeros always come in conjugate pairs. Remember, conjugate just means switch the middle sign. But if you want to store that one in and check the other answer from quadratic formula, it doesn't take you but 5 or 10 seconds. So 3 minus I over 5 also makes the original equation equal to 0. So consider doing that on the last 6 questions. The last thing I need to tell you is on these 6, some of these are not in standard form. So if you start on 37 and say this is A, B, and C, that's not going to work out for you. You can only quickly pick out A, B, and C if it's in standard position. So you need to move everything to the left or everything to the right. Just whatever you think looks easier is fine. Oops, that's a B plus. So make sure you do that before you try to pick off A, B, and C and throw it in the formula. Okay, so I've got 6 of those I'd like you to do, and I'd like you to go back and do those, I think, 8 other simplifying radicals. So go ahead and move forward on that. So if you guys have any questions, you can get that cleared up today. And then if you did not turn in 102, 103, and 104 in the Google Classroom before you came to class, just make sure I get your hard copies before you guys leave today. So worry about this first. I'll leave the agenda up here so that you remember what to do when you finish with that. But that's the last thing I've got for you, and you guys got about 40 minutes to do it, so should be able to achieve that with no homework. Sign out and take the pass, please. Now, this will probably be the only day we look at quadratics, solving quadratics specifically. We'll look at some graphing and stuff later, but just make sure that you're asking for some help here if you're getting stuck on any of them.